Today we're going to be talking about chirality, R or S configuration, and discuss a little bit about Fischer projections. To start, chiral atoms are simply atoms that are bonded to 4 different groups. In OChem, we are usually looking for carbons, but it can be other atoms as well. You do want to make sure to include implicit hydrogens when looking for chiral atoms because they may be one of the groups on a chiral atom. Look at this first molecule and add in all of our implicit hydrogens. These carbons on the end are going to have 3 implicit hydrogens. And the ones in the center we are adding based on the amount of other bonds that they have. Now, the chlorine is not chiral because it only has 1 bond. These 3 carbons are also not chiral because they are connected to multiple hydrogens, so they do not have 4 bonds to 4 separate groups. Now, the carbon in the middle, let's examine what it's bonded to. It's bonded to a chlorine atom, which is 1 group, an ethyl group, a 2nd group, a methyl group, the 3rd group, and a hydrogen, the 4th group. So there are 4 different groups that it is bonded to. Thus, that carbon is chiral, and it is the only chiral atom in this molecule. On our second molecule, let's add in our implicit hydrogens. The moment we add multiple hydrogens to a carbon, we can rule out that carbon from being chiral. They are not chiral because they are bonded to multiple of the same group, which is the hydrogen. Now, for the carbon we only added 1 hydrogen to, let's look at its 4 bonds. We have a ethyl group on that side, a methyl group, another methyl group, and the hydrogen. However, we have 2 methyl groups, so this carbon does not have 4 unique bonds. Thus, it also is not chiral. None of the atoms in this molecule are chiral. A word to describe such a molecule with no chiral atoms is achiral. For this molecule, we do not need to add in any implicit hydrogens. Another way to rule out an atom being chiral is if it has a double bond, because then it is only attached to 3 groups. Now for the rest of the carbons, we just have to look at the 4 groups it's bonded to. For the carbon on the very left, it's bonded to 2 hydrogens, so it is not chiral because it does not have 4 unique groups. The middle 2 carbons are bonded to an H, an OH, and 2 much larger but still different groups. And I'm denoting them here, 3, 4. So both of these carbons are chiral. Thus, we have 2 chiral atoms in this molecule. To introduce R or S configuration, I wanted to talk about our hands. They are mirror images of each other, but you cannot turn or rotate one hand to make it the exact same as the other. In the same way, molecules with chiral centers often have mirror images that are not the same molecule. We can denote them as R or S, just like we have our right and our left hand. An R versus S version of the same molecule is called an enantiomer, and it's a type of isomer, but we'll get into that in a later video. To determine if a molecule is R or S, we first have to look at the 4 groups and determine the priority. Atoms with a higher mass get higher priority. You then want to orient the molecule such that the 4th ranked, lowest priority group is facing away from you. You then determine the path from the 1st to the 2nd to the 3rd group to see if it's clockwise or counterclockwise. If it's clockwise, it's R, and counterclockwise means it's S. Let's do some further examples to explain this. I'm going to add in my implicit hydrogens to this first molecule and then determine the chiral atom. Now, the only atom that is chiral is going to be this carbon atom because it's bonded to 4 different groups. Now, I wanted to specify what these 2 bonds mean. This is a wedge and this is a dash. Now, the 2 regular bonds, the ones that are not thickened or have any weird symbols on it, those are going to be your plane on the paper. The wedge means that the bond attached to it is coming towards you, and the dash means that the atom is going away from you. When you have your 2 bonds in the plane, you want to make sure that your wedge and dash are drawn in the bigger angle. So this angle between the 2 regular bonds is smaller than this outside angle. So you want to make sure that your wedge and dash are drawn in the bigger outside angle, and this just has to do with like the tetrahedral shape. You want to keep the bonds as far away from each other as you can. So just remember this rule if you are ever asked to draw any compound. To assign priority to the 4 groups, you want to start at the chiral atom and go out 1 atom to each of the 4 groups. So that means we are looking at, if we go this way, the Cl, the hydrogen, a carbon atom, and another carbon atom. Now we assign priority based on mass. The heavier the atom, the higher priority it gets. So we know that from these 4 atoms, chlorine is going to be the heaviest one, so that gets first priority. And the hydrogen is the lightest one, so that gets last priority. We're looking at 2 carbons, which have equal mass, so we need to do a tiebreaker. To do that, you look at the 3 atoms that the molecule, or the atom, is bonded to. So let's look at this carbon right here. It is bonded to 3 hydrogens. So under that carbon, we can write H, H, H. Now, the carbon right here is bonded to 2 hydrogens, but it's also bonded to another carbon. So under that, we can write 1 carbon, H, H. Now, you want to compare the mass of these 2 little triplets that we have. The carbon and 2 hydrogens is going to be heavier than just the 3 hydrogens. So this carbon is going to get second priority, and this carbon is going to get third priority. So now we have assigned priority for all of our groups. We want to make sure that the lowest priority is pointing away from us. The hydrogen, which is our lowest priority, is on a dash. So that already means that it is pointing away from us. We don't have to make any adjustments. Our next step is to determine the path from the first priority to the second priority to the third priority groups. So we start at 1 and we draw an arrow all the way around to the 3. Now, does this look clockwise or counterclockwise? It's clockwise, so this molecule is the R configuration. Let's do the same for this next molecule. I'm going to add in my implicit hydrogens real quick. The only chiral atom is going to be this carbon. The reason I drew the hydrogen on a wedge was because the OH was on a dash, and you can only have one group on a dash and one group on a wedge. So now that we know our chiral atom, let's assign priority to the 4 groups it's bonded to. So we're going to go out 1 atom on each group. So we have an O, an H, a C, and another C. So this is going to be similar to the first one, where we have a tiebreaker, but we can also assign our first and our last priority. The O is the heaviest, so that'll be our first priority. And the H is the least heaviest, so that'll be our last priority. Now, with the 2 carbons, again, we need a tiebreaker. So let's examine the 3 atoms that the carbon is bonded to. And the reason I say 3 is because it's already bonded to that chiral atom, giving it 4 bonds. So we just need to look at the other 3 atoms that it's bonded to. Let's just make this 3rd carbon, this carbon right here, and this 4th carbon, this carbon right here. So the purple carbon, it is going to be bonded to 3 oxygens. And you might be thinking it's only 2, just this one and this one. However, when we have a double bond, we count it as 2 atoms. So that's why we have 3 oxygens in total. The 4th carbon is simply just bonded to 3 hydrogens. 3 oxygens is heavier than 3 hydrogens, so this purple carbon gets 2nd priority, and this yellow carbon gets 3rd. The 4th priority is pointing towards us, but we want it pointing away from us. We have a little trick for this. Since it's in the exact opposite direction that we want, we determine R or S with the 4th group pointing towards us, and then we just reverse it. So the 1 to 2 to 3 looks clockwise. So we think it looks like R, but we need to reverse it because the 4th group is pointing towards us, so it is actually S. A little denotation that I like to use for this, or that I was taught with, was we write R, but then we actually draw an arrow to S. So we know that it's actually the S configuration. For the 3rd molecule, we don't need to add in any implicit hydrogens. The carbon in the center is going to be our chiral atom. So let's go assign priorities. Going out 1 atom in each group, we get Br, O, C, H. And here we have no tiebreakers. So we can easily assign priorities based on mass. Br gets 1st priority, O gets 2nd priority, C gets 3rd priority, and H gets the 4th priority. So let's write those in. Now, the issue is the 4th priority is in the plane. It's not pointing towards or away from us. In a case like this, you want to switch it with the 3rd priority group, determine R or S configuration, and then reverse it to get the original molecule's configuration. So let's draw what it's going to look like switched. We have the H pointing away from us, which is exactly where we want it. Let me rewrite in the priorities. So we are going to determine R or S of this above molecule, and then reverse it to get the actual R or S configuration for the molecule that we truly want to figure out. So 1 to 2 to 3 is counterclockwise. So this molecule looks S, but we are going to reverse it to actually get R for the molecule that we're actually working with. Now, Fischer projections are a new way to depict molecules with a tetrahedral shape. All you need to know about these is this little intersection represents a carbon atom, and if you are on the sides of the carbon atom, like this H and OH, you are a wedge. So that means that those 2 atoms are coming out to you. And if you're on top or bottom of the carbon, then you are dashes. So that means those are going away from you. So an easy way to just kind of denote this is saying the same thing as this. This is all a Fischer projection means. The two groups on the side are coming towards you, and the two groups on the top and bottom are going away from you. We can also determine R or S from these projections. There are no atoms here, I just arbitrarily gave priority rankings. So let's go ahead and figure this out. I always like to draw in my wedges for the two groups on the sides, and then that helps me remember that the two groups on the top and bottom are actually on dashes. So our fourth priority is going to come towards us, so we're going to use the same trick as we used for the second example we did. We're going to find the R or S configuration of this molecule and then flip it, because when it's flipped, that actually shows us what the configuration is with the fourth group pointing away from us. So mapping out 1 to 2 to 3 looks like this. So the molecule looks like it's R, but it's actually S because we reverse it. So we actually determine RS configuration based on or when the fourth group is pointing away from us. Now for the second molecule, I'm going to draw in my wedges again, and that helps me remember the top and bottom are dashes, so they're going away from us. And we have the fourth group on a dash, so it's already going away from us. So we can figure out configuration as normal. That looks counterclockwise, 1 to 2 to 3. So this molecule has an S configuration. Thank you for watching.